Okay, so I'm going to cover mostly the software attributes of CXL, mostly what's available today as opposed to looking at pooling, tiering, all those solutions. So let's look at what we have today. And if I have some time, I'm going to show the demo as well. I will cover two aspects of the software development. One is how do you consume the CXL memory buffer within the context of application managed. The other one is kernel managed. So there are two different ways of consuming CXL memory buffers. I'm going to cover both of them. Before I do that, I want to actually show you the key things that are actually needed to basically get the CXL memory buffer provisioned and operating system actually seeing that as the memory capacity before you can actually consume that in the application space. So there are a lot of details, and I tried to synthesize that into as simple as possible. But needless to say, we spent almost 6 months to get that to work. So there are a lot of nuances that we need to think through to actually get that to work. Last but not least, I will cover the CXL benchmarking because as part of the SDM effort, we really would like to actually consolidate some of the benchmarking that we really would like to drive within the context of CXL memory buffers and software-defined memory. If time permits, I will actually show the live demo, and this is probably pretty huge risk, but let's see what happens. The CXL 1.1 usage model. So you heard about 3 different types of usage models, type 1, type 2, type 3. In type 2 and type 3, notice that there is a CXL.mem protocol implemented. So you can essentially expose, if it is a type 2 device or a type 3 device, you can actually expose CXL memory to the host operating system, irrespective of whether it is in type 2 or type 3. Right? That's a key thing to remember. Now, to provision the CXL memory, so first and foremost, you need to have either type 2 or type 3 device connected to the platform. So that's number one. And then the firmware. In the host firmware, you need to have lots of configurable knobs that you need to worry about. The key things is it a by 4 device? Is it a by 8 device? Is it by 16 device? Gen 5 capable? There are certain CXL specific constructs like security level. So you will essentially have to go focus on setting up the BIOS knobs to be able to say the CXL card can get trained successfully. Once the card is trained, you have to actually add, program the source address decoders for the CXL memory address space so that when there is a CXL traffic coming in, it actually can route the CXL transactions to the CXL buffer, right, in the platform. So there is a source address decoder programming. The critical one is really the ACPI tables. I know you've heard about ACPI tables before. There is the CXL early discovery table that actually shows you the register space. So the Linux operating system can actually discover, configure, do all kinds of interesting things. SRAT and SLIT actually give you the NUMA domains, the distances among NUMA domains, including memory-only domains. And then HMAT, which includes the bandwidth and latency attributes of the CXL memory buffer. So it's extremely important that the host firmware actually configures these ACPI tables, hands it over to the operating system. So that's a very important construct that host firmware actually has to do. Last but not least, there are 2 attributes in the CXL memory buffer, memory map, that actually decide how the memory is actually bubbled up to the operating system and how operating system actually sees the memory and configures the memory when it actually boots up. There is a special purpose memory attribute. If the firmware actually tags that as a special purpose memory attribute, Linux operating system basically configures that as a DAX device, not as a conventional kernel managed memory. If it doesn't tag that as a special purpose memory, for all practical purposes, Linux operating system sees that as another NUMA domain, memory-only NUMA domain, and does the provisioning just like any other host DRAM, memory domains. So when it comes to the operating system, so the memory configs, conventional memory, where kernel is managing it, or the DAX device, if it is a special purpose memory. There are 2 things that you can actually do. Once the operating system boots, when you have the DAX device, you can essentially override the behavior through the kernel command line parameter. We use this very extensively for testing. If you use the no soft reserve in the kernel command line parameter, that bit is actually ignored, treats that as a kernel managed memory. So you could override that behavior instead of actually going and configuring the DAX device. The other one is DAX control. It's a very nifty tool. This is part of the NDCTL GitHub repo, where you can actually promote and demote in and out of the system RAM. So this essentially gives you a way to configure the memory into system RAM or DAX device and vice versa after the operating system boots. And of course, you heard quite a bit about the kernel tiering. If you have multiple pools of memory, host DRAM capacity, the bandwidth and latency attributes are different from the CXL. If you have DDR4 backed device, it will be different from DDR5. So the kernel tiering actually plays a significant role in actually managing that as the unified virtual address space. And then of course, last but not least, for you to actually deploy CXL memory buffers, how do you know whether it is a CXL memory buffer or not? So you need command line tools. Just like NVMe command line tools, you need that kind of maturity with the CXL buffers. How do you know whether it is a memory buffer or the accelerator? Is it type 1, type 2, or type 3? There are a lot of things you can actually inspect the device through the mailbox commands. So all those command line tools are also important from an end-to-end solution perspective. Once the memory is exposed, then you have two different ways of consuming. One is through the application managed memory, where application owns completely managing the CXL memory buffer, or the kernel actually manages transparently to the application space. Those are the two different constructs. So let's take a look at application managed. So I have three different examples on how we can actually consume within the applications. Fairly simple. If it is an application managed CXL memory, for a basic way to consume the CXL memory is open the device, do the memory map, and then you can actually read and write into that virtual address space as if it is owned by the application. And then you essentially do the unmap and then close that file descriptor. It's pretty simple. It's extremely easy. It's just a matter of 10 minutes for you to actually write the program, start consuming the CXL memory that is exposed through the DAX device. Now, while it is simple, it's not enough. There are a few things that you immediately come to your mind. How do you know the size of the device? So you essentially can't, programmatically, if you want to look at the size of the device, then you essentially have to use the libndctl provides a way to actually look at all the devices, regions, and the capacity, and then you plumb that. Or you can use the sysfs interface, one of those two, right? But even then, in a multi-threaded environment, this is not going to be suffice. So there is the memkind library. Now, what this does is it essentially extends the JE-malloc, which is a very popular heap, user extensible heap manager, that you use the JE-malloc hooks that to extend and expose CXL memory buffer constructs as well through those hooks. Memkind is basically a library that gives you that shrink-wrapped way to consume storage class memory, CXL memory buffers, or even HBM, and so on. If you look at what you see in the memkind actually has its own set of APIs. So first and foremost, you have to create whatever memory you have in the platform, and you have to create that using memkind create call. In this case, I'm showing pmem because we just don't have the CXL constructs yet in the library. But pmem can manage the DAX device also, so the demo will work irrespective. And then you essentially do the malloc. Memkind malloc is the call that you have to use. Instead of regular malloc, you have to say memkind malloc for a given memkind. Use the way you are using the virtual address space, using load store semantics, read and write into that address space, and then you free, and then you essentially destroy. Right? So that's really the sequence of things. But the good thing about this one is that it is multi-threaded because JE-malloc is multi-threaded. So it scales well. So you get all the fringe benefits of JE-malloc. And once you extend that to the memkind, you essentially get to take advantage of CXL memory buffers. So that's another way to consume. Third one, obviously, you need persistence, let's say. What do you do with the persistence? So you essentially have to look at persistent memory development kit. PMDK has been there for quite some time. It has different constructs. The example here shows only the basic foundation calls, things like how do you map the DAX device, and how do you actually read and write into the DAX device, and how do you persist using CL flush and cache line write back and so on. But there are higher level constructs as well in libp, in the PMDK, things like libpmem obj. It gives you the object based constructs for you to transparently use in the C++ programming languages. Again, the concept is very, very similar here with the exception of persistent call. So you open the device, map it, and then you essentially use it the way you want to do, and then when you want to persist it, call pmem persist call to essentially make sure that the data that is actually sitting in the caches gets flushed and it gets persisted. So that's the PMDK. So 3 different ways: basic mmap, memkind using a user extensible heap manager. Third one is persistence through PMDK. So those are the 3 different options available, and of course you can write your own on top of that, right? So let's take a look at the kernel managed CXL memory. Now, so essentially in the kernel managed, you have 1LM and 2LM memory that is attached to the platform, and you can actually manage them transparently through kernel layer. Now, everything is actually surfaced as a virtual memory address space. So as far as your application is concerned, it is basically consuming virtual memory. Behind the scenes, kernel is actually managing the tiering aspects, migrating the hot pages into the faster, migrating the cold pages into the second tier or the lower tiers, slower tiers. So the transparent data migration happens behind the scenes, but as far as the application is concerned, it is consuming the memory through unified virtual address space. There are 3 different ways of consuming. One is obviously don't change an app, let the kernel manage the tiering, and everything goes, happens behind the scenes. The second one is, no, the application wants to consume CXL memory buffer directly and use the NUMA control as a way to consume the CXL memory, and I will show the demo. The third option is that you can actually integrate NUMA aware APIs into the mix, so you can actually allocate and free in the specific NUMA domains, memory only domains, right, using libnuma. So those are the 3 different ways of actually consuming memory through the kernel, transparent all the way to NUMA aware integration. Okay, so now we talked about both application managed and kernel managed. How do you actually bring these 2 things together? Now, Manoj actually talked about Cachelib in the morning. Essentially, it's an in-process caching engine that is highly performing, highly scalable, multi-threaded, C++, thread-safe API, right? It essentially has the KV interface, right? You can actually find, allocate space into the cache. You can actually insert or replace the item in the cache through the Cachelib API. Of course, the APIs are not comprehensive. It is just a sample. But the good news about Cachelib API is that it manages both memory tier as well as the storage tier transparently, so you don't have to programmatically control anything. The only thing that you control is the policies on how you move the data back and forth, right? So that's the advantage. So how do you take advantage of Cachelib? There is a cache bench benchmarking tool that has different profiles you can use to benchmark your CXL memory buffer. There are 2 ways we have been benchmarking. One is we can use the NUMA control and directly point cache bench at specific CXL memory buffer, and then you consume it. The other way is let the kernel tiering actually do the work, and then you actually do the benchmarking to see how the kernel tiering is actually working between host DRAM and the CXL memory buffer. Right? Those are the 2 different ways. There is work actually in flight to figure out the best way to extend the second tier as the another memory tier as opposed to block tier, but it's still ways out. So let me give you a flavor of the working demo. So there are 2 portions in this demo. First and foremost, remember I talked about the end-to-end provisioning where the device need to be connected to the platform, firmware has to detect, operating system has to see that as a buffer, and it has to show that there is a CXL buffer in the operating system. So we are using the pre-production CXL card, Intel CXL card on the Intel Sapphire Rapids pre-production platform. This essentially goes through all those 3 steps. The first one essentially is if you look at the right hand side, you plug the card. onto the platform. This is the card. This is the by 16 PCIe Chem form factor card. You have to configure the BIOS, otherwise it's not going to enumerate that as a CXL buffer. And then you reboot the server once you configure the BIOS. I know you cannot see that remote, but at the bottom it says there is a CXL buffer that it detected. And then it essentially goes through the SAT programming and all the ACPI table stitching and everything else, and boots the operating system boots, and then it shows that it is a memory buffer. That's a FPGA based. And then if you look at the capacity, you can actually see the capacity. So that completes the entire firmware provisioning, OS provisioning, to be able to see the card that is actually running in the platform. Okay, so let me show you the real quick demo. So here is the DAX device. This is a single socket platform. This is the Sapphire Rapids single socket platform. I'm going to show you 3 different tools. First one, I'm going to actually take the PMDK tool, which is called DAX IO tool. This is the tool that's part of the PMDK that essentially goes and resets entire CXL memory buffer content to 0. So, and it takes less than few seconds. So in this case, it basically reset the entire buffer content to 0. I'm going to read this. Basically, this is the mmap, dump the content in the hex, and then get out of it. Right. So I'm going to read. So here you can see that pretty much the buffer content is empty. Right. Then I'm going to use the memkind tool example code. So this memkind malloc code basically is doing the memory map of the DAX device, doing a couple of malloc calls, and then closing them. Okay. So it did a couple of malloc calls, and let's actually try to dump the content again. And you can see that on the right hand side, it says hello world from pmem string. Right. So PMDK tool to reset, simple mmap tool to read and dump, memkind example to essentially do the malloc. Right. So you can see that those 3 tools are actually working. So let's take so right now it is a DAX device. So I'm essentially going to promote this as the kernel memory. So using the DAX control. So this is essentially promoting this as the kernel memory. So if you look at the kernel memory, this is the logical memory domain that is essentially a CXL memory buffer. On the right hand side in the NUMA stat, you can actually see node 1. Node 1 is basically logical memory only domain. This is the CXL memory buffer. You can see that the memory free is actually 64 GB. This is the 2 DDR, 2 channel, 32 GB capacity buffer. Now, what I'm going to do is I'm going to run the CXL cache bench. Essentially, it is going to treat node 0, node 1 memory as uniform, and it is just going to blast it off and consume, believe somewhere around 50 or 60 GB capacity. Notice that on the right hand side, the mem free keeps going down, both on node 0, which is the host DRAM, and node 1, which is a CXL memory buffer, and it will keep going down. Right. And then it will start actually doing the throughput testing. So hopefully you got the feel for 3 different tools that are the development kits that you have to consume the CXL memory in the application space, the kernel tiering, dynamically promoting and demoting, and be able to actually use CXL bench to actually test the CXL memory buffer performance attributes. Okay. Okay. With that, I wrap up my session. So while this is essentially what's on the truck, there are a lot of things that are needed. Obviously, as I alluded to before, DAX support in the PMDK is very weak. Memkind support is it doesn't have very good DAX support. So in the application space, especially if you want to have user space heap manager that consumes CXL memory, I'm talking about a very simple CXL memory attached to the platform. I'm not even talking about tiers. there has to be a way to evolve these software stacks to consume. That's one of the focus areas we need to collectively work towards. Kernel tiering, right? There are a lot of interesting challenges in the kernel tiering. How do you discover different types? How do you actually move the data? How do you actually track the pages that are hot and cold? How do you migrate them? What kind of policies you want to have? And all the tool chains around it, still evolving, especially in the Linux space. So the kernel tiering also has to requires a lot of work, right? So collectively, we need to work together to enable CXL memory buffer use cases, for production usage, not just in the lab. With that, thank you.